Okay, could I ask a few more folks to turn on your webcams, please? All right. Thank you so much. All right, let's get going again. All right. I'm looking at some of the comments about my beard. So I look older with the beard. Yes, Mehtab, I look older with the beard, which is why I grew the beard because I was coming out of my PhD and I was afraid, when I'm looking for a job as a professor, I may look like too baby-faced to be a professor, so I grew the beard quickly, right? And then when I got my job, off, and then I got married, off it came. It's like, don't need it anymore. So look for the next opportunity, next advantage I can get from it. All right. So let's get back to it. So I just want to give you a quick tutorial overview of how to use this package to do both PLS for composite structural equation modeling and CBSEM for uh, common factor-based structural equation modeling. Right? And here's a quick rundown of how to use the tool, and I'm just going to give a very simple homework assignment where I'm just going to try to ask you to use the tool, see some estimates, and it'll give you a flavor of all the things we've been doing over the past several weeks with like moderation and other things as well. All right, so let's get started. Oops, excuse me. So, first of all, to install this package, you just do install packages and seminar like you do for all your other packages, okay? So that should not be a big problem. Um, let's talk about how to use it, and I'm going to start with composite-based models, all right? So to use it, simply load the package using the library function, and then load your data up. Right, let me see if I have an example of it here. Let me switch to this one. Excuse me, this one? Okay, I think this should be it. Yes. So after you've installed it, just get the library and let's load the data up. Okay, and this data now is going to have 141 variables. I'm not sure, but I think I gave them all to you before. If not, this is the new data set is going to have 141 variables. Okay. Now, how do we define this model? So this model has 4 constructs, right? It has 4 constructs, and each construct is a composite. In this case, let's start with composites, and they're measured by certain measurement items. Okay. So the first thing we're gonna do is define our measurement model. Like, what are these constructs? And the way we do that in the seminar package is we're going to use a function called constructs. So this begins here, constructs, and it goes all the way down to here. All right. So in the constructs function, you just define all your constructs. That's all you do. Excuse me. Um, and you can just list them out, separated by commas. Okay, separated by commas. And each construct, you just define what it is. So in this case, I'm going to define each construct as a composite. So that's another function called composite. Within composite, I give the name of the construct that I want to create. So REP, INV, SEC, trust, just kind of the way you see in this picture, REP, INV, SEC, trust. And then for each of these constructs, we can define what are the items that they're going to use. So if I take a quick look at the names of the items in my security data set, you will see that, for example, reputation or PREP, perceived reputation. Where is it? Where is it here? Oh, so many things. Here it is. So it's measured by 4 items, PREP1, PREP2, PREP3, PREP4. And there's 2 ways you could write that. You could either write it as a vector, PREP1, PREP2, oh, excuse me, PREP3, PREP4. So that's one way. You can just define that this composite called REP, reputation, has these 4 items. That's it. Okay. Now, a lot of the time, your items are going to have the same name with a different number at the end. And we made a little helper function that lets you describe that very quickly. You can just say you have multiple items. So multi-items is a function to say that this construct has multiple items. They all begin with PREP, and please append to them the vector 1 through 4. So multi-items 1 through 4, if I just run this separately, if I just run multi-items PREP 1 through 4, it actually just creates the vector PREP 1, 2, 3, 4 for you. That's all it does. All right. And similarly, for perceived investment, for the security construct, or privacy security concerns construct, and then this trust composite, this composite called trust. All right. So there we are. That's the 4 composites, and we put them into this constructs function, and that defines the 4 constructs that we're going to work with. We're going to hold on to this definition. I'm going to store these constructs in a variable called SECMM. Okay. And so if I run this whole thing, I've got something called SECMM. Okay, and I'm not going to go into look into it too deeply, but it basically stores information about all my constructs and their items and so on and so forth. All right. The next thing to define is the structural model. So the relationships, remember the structural model is relationships between the constructs. In this case, I have relationship between reputation and perceived investments to security, and I have relationships from security. I have a path from security to trust. Okay, so I have 4 paths. I have 3 paths: from reputation to security, from investment to security, from security to trust. So 3 paths. Those define the relationships of my structural model. Okay, and if you look at the code to do that, it's pretty easy. We made a function called relationships. You just define all your relationships. Okay, and within it, you define the paths. All right. So for example, this, I say I want a path from security to trust. That models this path right here, from security to trust. Okay. Okay. Give me a second here. All right. What about these 2 paths, from reputation to security and investments to security? I could do the same thing. I could say paths from reputation to security, paths from investment to security, or I can just do them both together. Here, I've said I want paths from reputation and investment. I've just defined them, the from as a vector, to security. That's it. And that creates these 2 paths, from reputation and investments to security. So this defines the 3 relationships in my structural model. And again, I'm going to store it in a variable that I'm going to, all right, so SECMM is my security measurement model, and SECSM is my security structural model. Right? Great. And that's the code is right here. That same measurement model and structural model. Notice one thing that I worked on with students when we were creating this package is I wanted the syntax to read just like the words we used to describe the model. So we were saying that we want composite constructs that are measured using multiple items. We want relationships between constructs with paths from certain variables to certain variables. So we made the syntax as naturally readable as possible so that it really matches the language that people creating these kind of structural equation models are using. All right. And I think this is one of the reasons it's become so popular, because compared to many of the other packages, a lot of teachers are finding that students and themselves, researchers are finding they can kind of read this very clearly from top to bottom and know exactly what the model does. All right. Great. And then we can estimate this whole model. That is, we can estimate all the weights and these structural regression coefficients, these betas, we can estimate them all together using this estimate PLS function. Remember again, PLS is the technique we're using to estimate composite models. All right, so we simply define we simply asked it to estimate it like this. And excuse me, sorry about that. So we're telling it that we want to use, please estimate using PLS. We provided the data that we have, and we define the measurement model. We're going to use the constructs we defined before. And the structure model, we're going to give it the relationships we measured before. All right. And that's it. It has now estimated this model. Okay. You can look into this SEC PLS and you'll see a lot of things flying by you. All right. It's a little too much almost. A better way to get a report is to just call the summary function on it. Just like with the LM function we did for linear regression, if you run summary on it, you get a whole bunch of helpful things. So if you say, let's run a summary of this estimated PLS model, and we're going to store the summary in this report variable, SEC report. Okay, and SEC report is going to have a lot of helpful things. You just have to look into it. For example, the thing that we all want to see right away, what was the relationship between our constructs? So the relationship between our constructs is kind of defined, is told you here. We're told that reputation now these are standardized regression coefficients, had a 0.35 coefficient on security, and investments had 0.28 beta on security. So that's this relationship here. This was 0.35 and this was 0.28. Okay, and security had a relationship on trust of about 0.6. Right, so that's this relationship here, 0.6. And I also give you an R squared and a adjusted R squared. For now, I just have to look at the R squares to see what is the R squared of security and trust, because these two are dependent variables somewhere in the model. Right? So it's just as simple as that. If you were curious about these weights, okay, if you're curious about the weights, then these are the weights. Now, these weights are similar in concept to like eigenvectors, but the difference is in PLS, these are not components. They are composites, but they're not components, meaning reputation, investment, security, and trust don't have to be orthogonal to each other. They can be related to each other, all right? And all I report is the weight of each of these items on the construct they are reported, that we specified them to have a relationship with. And you can think of these weights, again, as regression weights. So the scores of REP will be literally these items multiplied by their corresponding weight and added together. And that will give you the scores of REP. Similarly for investment, similarly for security, similarly for trust. It'll be these items, each weighted by this amount, and then added together. All right. And in fact, I can also get the composite scores. So these are the scores of each respondent. I forgot how many respondents I had. I think about 400 or something like that. Each person who replied to my survey, this is their score on reputation, on investment, on perceived investments, on their perception of security and privacy, and their perception of trust. All right, so these are their scores. So to be clear, this is a composite model, but these constructs are not orthogonal components the way they are in PCA. All right. Instead, PLS just looks at the items that belong only to the construct that they're specified to belong to. All right. Okay. And that's composite modeling in a nutshell. One thing that I've not shown in my slides, and I regret because it's kind of a fun thing, is that once you have estimated this model using estimate PLS, you can ask to plot it, let me make the space a little bit bigger before it complains. Oh, this may ask you to install uh, a library to do to draw the path diagrams and things. Let me just install that. It'll only ask you that one time. Okay. Give it a second. It's going to install everything. We don't install it by default because some people just do not want to see visualizations of their path model. They don't want to see any plots. So for those people, they don't have to install this package. All right. Oops. Give me a second. The model will be, so there's the model right here. The model this time does not show up in my plots. It actually shows up in a separate tab called Viewer. And here it is. Here's my investment, reputation, security, and trust. You can see these are showing you, actually they're showing it to you as loadings, but it actually should, but you can think of the weights separately. And then these show you the regression coefficients from between the constructs. All right. Going to make that smaller again. So, excuse me, these are composites, all right? Now, even though they're composites, one thing you could do, and let me see how I can get it, SEC reports, dollar, loadings, yes. Just like in PCA, where you can convert the eigenvectors into loadings, even with composites, you could look at what the loadings would be like if that's what we were interested in, all right? But just to realize these loadings, even though I'm calling them loadings, this is not a factor. We're just kind of post hoc estimating what would the loadings be like, even though this is a composite, all right? And these loadings really tell you the correlation between each item and the corresponding composite. Right? Cool. So that's how you make composite models. Pretty easy, I think. All right. Much easier than a lot of the other packages out there. That's my opinion. Right. Cool. I'm not going to go into the details of how PLS actually works. In previous semesters, again, I went into more details, but I just want to kind of keep this light and give us a softer landing for this semester, all right? So all I'm going to ask you to do for your homework is to just create a couple of structural equation models like I'm doing right now and just report a couple of interesting things. So you can get the weights, you can get composites, you can get pads, all right? Oh, and one thing about PLS though is that it doesn't give you any p-values or t-values. In fact, it does not compute standard errors for example, these beta coefficients, these regressions between my concepts. I have these regression coefficients explaining how reputation and investment affect security and how security influences trust. These are standardized regression coefficients, but PLS cannot generate standard errors, unfortunately. The technique is an iterative technique, not a classical statistical technique, so it does not generate standard errors. If I want to get standard errors, we got to go back to our good friend, the bootstrap. This time, because I know people will all want to bootstrap it, we just made life easy by just creating a bootstrap function. It's literally called bootstrap model. And if you bootstrap the model, so we take the model that we estimated. This is the estimated model that we got from running estimate PLS, right? And we say, let's just bootstrap this model 1,000 times, all right? And this will take a little while to run. This is not super quick because this is a complex model. This is much more complicated than the regression models that we've been looking at earlier, all right? So it takes a little bit longer. It really takes a little bit longer. One of the things I'll talk about in next week's lecture, which is again a fun lecture with no homework associated with it, just get a cup of coffee, come join us, and we'll just talk about some interesting topics in computation. And one of the things I'll talk about next week is that there is a lot of computation that takes a lot of time. And when you're running your own analysis, you will often want to rerun your analysis many, many, many times with different parameters, different assumptions, and it gets really painful to wait for things. So one of the things I'll talk about next week is how to make these kind of operations run faster. And in particular, what I'll explain is a lot of what we're doing with computation, everything we've done so far this semester, is not really fully utilizing the power of your CPU. Your CPU has multiple cores on it, meaning it has many heads it can think with, but all the code we've written so far is only using one of its many heads. For example, my CPU has 8 cores or 8 different heads to think with. We're only using one, which is what takes it so long to finish a lot of tasks. Okay, and one of the things that we did is that we also um, allowed you to use as many cores of your CPU as possible. So I think this is, maybe it was already using 8 cores. I'm not sure. Maybe it was already using 8 cores. I'm actually not sure. But you can actually use all the cores of your CPU. Now, how do you, now I've kind of made the code to be able to do that. Oh no, I tried to kill it and it wasn't happy that I tried to kill it. All right, sorry about that. Don't tell me I have to run it all again. Boo. But one of the things I'll talk about next week is how can you take your code that you're writing and make it run on multiple cores. So I will do that, okay? Um, is boot PLS defined? Yes, fantastic. I still have it here. Oh, excuse me. Yes. No, what are these? Why are these open? Excuse me. And let's take a summary of this bootstrapped PLS. No, I think it didn't finish running it properly. Okay, so I shouldn't have killed my RStudio. Sorry about that. But I ran these results for last night, so I'll show you the results I got earlier, rather than making you wait for the whole bootstrap to run again. So these are the results I got. Essentially, um, it tells you now for each path, for example, the original estimates, the mean of the bootstrapped paths, the standard deviation, the t-statistic, and the 95% confidence interval, the lower bound and the upper bound of the 95% confidence interval. Okay, so you can get that through bootstrapping this model. Okay, now unfortunately I have. Let me just close these RStudio windows. I'll try to open back up. This was from today's class, so, and I'll just try to open up RStudio again. All right. So anyway, so this is bootstrapping. Unfortunately, we have to bootstrap the model. It does take a lot of time, and okay, and that's how we kind of get our inferential statistics for composite-based modeling using PLS, using seminar package. All right. Okay, so that's composite modeling. Anything else? Oh yes, a couple more things I wanted to explain to you. One was we can do interaction terms. All right, and interaction terms in structural equation modeling is a little bit messy, but let me explain to you how it does it. It's exactly how you would think it would do it, but it's a real mess to look at. Okay, so let's say for example we want to change our model so investments moderates the relationship between reputation and security. So the relationship in reputation and security will depend on the level of investment, of perceived investments, okay? When we model this in structural equation modeling, the way we have to do it is the following. If these two constructs, reputation and investments, are going to have an interaction with each other, we need to create a new interaction term, which essentially is a multiplication of these two things put together. And one of the ways it's done commonly is we take each item and multiply it by the corresponding items. So for example, x11 will be multiplied by x21, by x22, by x23. So we create, for every combination of the items of these two constructs, we will create a new product item here. So each of these items is multiplied by all of these items, and every combination produces a new item. It's a big mess. And then this interaction construct, so we basically create an interaction term just like we would do in regression. This interaction term here is basically going to take all these items together. All right. Now, as you can imagine, we're going to have really big problems with multicollinearity when we do this, because now this interaction term, it's each of its items, which is a product of the items of the other two constructs. Each of these items is going to be heavily correlated with the items of these two constructs. So this interaction term is actually going to be heavily collinear with the construct's reputation and investments. What can we do? Well, what we can do is we can, use the techniques we learned before. We can scale or mean center the items, okay? Or even better, remember our good friend orthogonalization? We can take each of these items, we can take each of these product terms, regress it over the terms that were originally used to produce it, capture the residual, and use the residual in place of the actual product. All right? Whew. How are we going to do that for all these items? You're going to be sitting here forever. Don't worry, we thought of that for you. So one of the things the seminar package does, oh, excuse me, it's still not loaded my R. Where's my RStudio? Oh, there it is. Okay, there's my RStudio. So let me make sure, like, I've loaded some of these things. Oops, excuse me. Library seminar. And I've got to, I just got to run this code again one time. All right, so, okay, it's working. So now how do I define this, this very big, messy interaction construct and orthogonalize all these items one by one? Oh my God, it'll take forever. And in the other R packages, you literally had to do that by hand. It took forever. So one of the things we did in seminar is we created this, we do it for you. So this time I'm going to define a new measurement model. Excuse me. I'm going to define the four constructs just as I did before as composites. But this time I'm going to add a new construct in there, which is an interaction term. And it's going to be an interaction between the independent variable reputation, the construct, and the moderating construct, perceived investments. And look at this. I can tell it, please use that partial orthogonalization technique that we've been talking about in BACS. All right. So there's my constructs. The relationship now is going to be from reputation and investment, and the interaction. This defines the interaction of the two constructs and the interaction of reputation and investments on perceived security and privacy. And the next path is the same. Okay. So essentially, again, with these two lines of code, I have now specified four paths from reputation and investment and the interaction term to security. That's three. And from security to trust. So here's the three paths from reputation, investment, and the interaction to security, and the path from security to trust. All right. And now I can estimate this. And I can get a summary of this interaction. So here I can see the path coefficients, and I can see that reputation to investments. Oh, it has a very small interaction. It may not even be significance. Okay. And I'm not going to describe reliabilities. For those of you who are really into structural equation modeling, I can maybe hold a little workshop on it over the summer or anytime you wish me to. I'm more than happy to describe it, but I don't want to do it in class this semester. And last of all, yes, unfortunately, if you do want to get, like, for example, this interaction term is so small, I wonder if that is sometimes it's going to be 0 when I bootstrap it. So all I can do is bootstrap it. All right. And this is going to take a while to run. It's a little bit complicated. Okay. So you essentially have to bootstrap the model and then see a summary of the bootstrap. Okay. Let me drink a glass of water, and while I wait for that, and see if there's any questions. Yeah, Guild is asking me, is the structure of the data that I provided in previous weeks different from this week? Guild, I think so. I think this week I have to provide you the data for reputation and other things as well. So sorry, I don't think I provided you this data, this full data set yet. Okay, so please bear with me, and after today's lecture, I'll put that up online along with the homework assignment. Okay. There's also another question that came in during the break, just directly to me, which is, we have class next week because next week I think is going to be Dragon Boat Festival, right? So what I'm going to do is I'm going to try to reschedule the class to, let me ask you, is Tuesday a holiday? No, Monday's a holiday though, right? Next Monday's a holiday, right? If next Tuesday is not a holiday, I will try to set up a time on Tuesday. Now, I realize that some of you may have other classes on Tuesday. So what I will do is I will make an evening session on Tuesday to do this class. Okay, so I apologize about that, but it'll probably be an evening session where I'll just go through some fun programming topics and topics that might be relevant for those of you who are really interested in going into a data science future, some tools and things that you should know and have in your tool belt so that you can really write the kind of code we're doing this semester more professionally as well. All right, great. So I'll set up a time. I'll talk to my TAs and I'll set up a evening Tuesday time, I think, but I'll let you know. For those of you who cannot attend on Tuesday evening, there'll be the YouTube video. I'll try to put up the YouTube video as well. But I do ask for those of you who can, please attend the Tuesday workshop. It'll be more fun if there's more people there. Okay. And so here is the whole thing. Don't look through everything. There's a whole bunch of things that researchers are interested in and keep begging us to add. The thing that we're really interested in is right here, the bootstrap structural paths, the structural model bootstrap. So you can see here, for example, the interaction term, its original estimate was about minus 0.07. But when we look at the confidence interval, the 0 is in that confidence interval. So we cannot say in classical significance terms that this is significant to 95%. However, so basically it means that this interaction is probably not very strong at all. Okay. All right. So that's how you do interactions. And what's really cool again is all that orthogonalization and stuff that we've talked about. You just have to tell it you want to do orthogonalization and it does it for you. So nice. All right. Okay, cool. I think I had maybe just one or two more things. I think I had just one more thing to mention today. Yes, which is, this is PLS. How do we do structural equation modeling with common factors with using this other technique called covariance-based SEM? It's a completely different technique to do structural equation model, which models all your constructs as common factors. One thing we did when we made this package seminar is that we made it extremely easy to write almost the same code for whichever model you're trying to do. So if you're making a common factor model and you want to estimate it with covariance-based SEM, all you have to do is this time define your constructs just as you did before, but this time instead of calling them composites, call them reflective. Reflective means that these items are reflective. Reflecting means it's like a mirror. It's showing you an aspect of the construct. So reflective is another way of saying it's a common factor. All right. So it's reflecting the meaning of the underlying construct. So we just define this as reflective instead of composite. That's all you got to do to set up your measurement model is just change the word composite to reflective. Okay. Let me jump to my code and see if I can do that here. Oh, I did that right up here. All right, so here is my model. This time, as common factors, everything is defined as reflective. All right. Earlier, my model SECMM, everything was defined as a composite. And actually, I have a little secret which is undocumented. You can actually take your composite model and just write as reflective, and this will convert the whole composite model into a reflective model. Ta-da, you're done. Okay, but oops, excuse me. Oh, hold on. Where did my RStudio go? Oh, I think I killed RStudio again. Excuse me, sorry. I think I accidentally hit the quit button and I quit RStudio. All right. Okay, as I'm loading that up, so you basically define your items as reflective. Okay. And that's to define the measurement model of a common to define a common factor model. Now, the last thing you've got to do is we cannot well, we could, but we don't want to estimate this using PLS. We want to estimate it using this other technique called covariance-based structural equation modeling. So when you run the estimate function, the new function to use is estimate CBSEM instead of estimate PLS. That's it. Okay. Oh, Yenyu is asking, what does a reflective model mean? Reflective is another way of saying I want these to be common factors. Okay, so why do we call it reflective? Well, for two reasons. First, the word factor is already a function in R, so we couldn't use the word factor here. Boo. So we had to give it a different name. And oftentimes, common factors are sometimes called reflective constructs because the meaning of this construct is reflected in its items. In English, when something's reflected in something else, we mean part of its meaning is in something else. Okay. Just like when you stand in front of the mirror, your image is reflected in the mirror. You don't get an exact 3D representation of yourself in the mirror. You get a 2D approximation of yourself in the mirror. So that's called a reflection. So similarly here, we said these items, they don't like exactly capture security. They reflect some of the meaning of security. So I hope that makes it clear. When we say reflective, I just mean common factor model. Okay. So reflective instead of composite, and then estimate with CBSEM. And when you do that, and I'm not going to run it now for the sake of time, when you do that, and you actually maybe I should do it because so let me kind of do it here. So let me oops, it's forgotten everything. I've got to load this library again. And let me see if I can do this. Okay. So now we are estimating it using CBSEM. It takes a while, but not too long. And with CBSEM, you don't have to bootstrap anything. Let me just get the summary of this estimation. And I think there's a paths, yes. And here it gives me the coefficients, just like I did before for composite modeling. Okay. There's my effects. You'll notice my coefficients are quite a bit stronger now. You'll also notice that my R squared has gone up. Modeling with common factors gives you a lot of these nice properties that you get a much stronger explanation. You may not get a stronger prediction, but you get a stronger explanation. And you don't have to run bootstrapping on this. This is a parametric technique that gives you p-values right away. These p-values are practically zero. Okay, this one is zero. So that's all you've got to do to do common factor models. The code I showed you earlier for interactions, It's the same. You just put the same interaction term back into here, and you can do interactions for common factor models. Okay. All right. So using the seminar package, doing composite structural equation models with composite constructs or with common factor constructs, the code is almost exactly the same. Another reason why this package is increasingly becoming popular, people are saying, wow, use the same syntax, not have to learn 2, 3 different packages to do the same thing. All right. We have one more question here. Jemming is asking, I'm wondering how can we do mediation analysis? I haven't shown you how to do mediation analysis, but let me just, and I'm not sure if I'll ask you to do it for the homework. Maybe I will. I can't remember if it's on the homework or not. But there is, so let's go back to our composite model. Okay. So in our composite model, oh, and I just want to get a summary of our composite model. Where was it? Summary of our composite model. Okay. All right. So we notice here that, and I'm just going to jump back here. In the summary of our composite model here, we notice that, oops, where am I? I'm a little turned around. I apologize for that. I have to go back a couple of steps. Right. So for example, reputation has an indirect effect on trust through security, right? And if we want to know the indirect effect, we just have to multiply the path from reputation to security by the path from security to trust. So if I multiply the path from reputation to security by the path from security to trust, I should get the indirect effect. That's all you got to do. Now, the issue comes with, well, what's the standard error of this estimates? Well, before, when we did this with regression, we basically used bootstrapping. And what we've done in this package is, let me just, I can't remember if I bootstrapped after I restarted it, so let me just bootstrap this once again. After you've done the bootstrapping for this model, we made a function that will calculate the standard errors of your estimate for you. And as soon as bootstrapping is finished, I'll show you how to do that, okay? So please give it a moment. And I think that'll be the last thing I'll talk about today. Okay. Yes. Bootstrapping for significance, interaction terms, common factors. Okay, and then I'll talk about the final class. Give me a moment while this is running. The bootstrapping is slow. It's a complicated model. Also, my computer's slowing down because I'm live streaming and I'm also I'm live streaming on YouTube and I'm also using Zoom at the same time. My computer is very overwhelmed. Okay, so let's look at this bootstrap model, and I believe there is a estimate specific. Is it no estimates specific. Yes, there's a function called specific effect significance. I don't know why we named it that. We're going to rename it in future, but you got to provide it the bootstrap model. You don't have to bootstrap it again. You just bootstrapped it. And then you tell it you're interested in the indirect effect from, let's say, reputation through security to trust. Ta-da! And that uses the bootstrapped results to tell you, here's the estimate of the two paths multiplied together. This is what we got basically, 2.213. When we looked at when we look at it across the bootstraps, then on average across the bootstraps we get a similar result. But here's the bootstrap standard deviation for this estimate, the t-statistic, and the 95% confidence interval. So Jemming, I think you were interested in kind of finding this indirect paths. This is how you would do it. Okay, what we had to do by hand in regression, we do for you right here. Okay, so. Um, Right. So Jiaming is asking, so the path, so this is a really good question, Shun. Let me show it on screen. He's asking, so the path that we build in the model is based on what we hypothesized or based on the domain knowledge by previous research, right? Yes, that's right. We are hypothesizing these paths. We believe these to be the paths. There could be other paths, but we're not going to just explore it through the data using this technique. I mean, you could just let everything affect everything. You can make a model like that, no problem. But the model that I'm showing you is based on some domain knowledge. It's hypothesized. Yes, that's absolutely right. So we're kind of following in the inferential hypothesis building methods that we saw with regression earlier. Okay, great. Okay, so that's enough of this for now. So that's how to do structural equation modeling, and I showed you how to do it with composite models, how to do it with common factor models. You can do mediation, moderation, and a bunch of other things I'm not going to talk about this semester. I want to keep it nice and easy and light, okay? So, but it really wraps up a lot of the things we've talked about in the previous weeks. So we've talked about how to create, regression-based models. These are all kind of similar to regression. But now we can create much more complex models than regression. In regression, you could just have one dependent variable and some independent variables. With this, you could have a chain of effects between mediators and define a very complex model. You can do mediation through that, obviously. You can do moderation through it, the way we saw in regression. And what's also really nice is, like we saw in PCA, you can also create constructs. In this case, these are not components, not orthogonal components like PCA, but these are constructs that are defined from items by some domain expertise. So we can kind of reduce this multidimensional data into just some smaller constructs based on our expertise. All right. So it kind of wraps up all these things we've talked about in the last two modules of this course about regression and dimensionality of data. And the structural equation modeling is a technique that just kind of wraps it all up together and allows you to do all of it at the same time. Okay. And that's what I want to conclude with this semester. Now, next week, I will try to hold one more bonus lecture, and this is the stuff that I'll talk about. Okay. I might spend a little bit of time talking about some of the some of the measurements that come out of structural equation modeling and whether it's good or bad. I might spend a little bit of time talking about that, but not too much. I do want to spend a little bit of time talking about degrees of freedom. Remember this thing, degrees of freedom? We keep talking about it with ANOVA, with regression, like here and there. We never really said what the hell is degrees of freedom. I'm going to go back to this topic of degrees of freedom, and I'm going to try to address this from a geometric point of view. So we're going to revisit degrees of freedom, and we're going to try to understand it geometrically, um, and just try to get an intuition of what it actually means. I'm sure you've heard of an explanation of what degrees of freedom means in other classes. I'll just give you one more interpretation of it, okay? And this time using more a geometric way of thinking about it than a pure statistical way of thinking about it. What else are we going to talk about? I'll talk about what to do when we have really heavy computation to do. A lot of the problems we're doing, even though it's not really that complicated, it takes a lot of time, and computation is very heavy. So we'll talk about how to fully utilize your hardware to do very intensive computations that take a long time to do. So we'll talk about, for example, how to use your CPU to its maximum ability to so if you have an 8 core or 4 core or 16 core CPU, how to use all the cores of your CPU and really use the full power of your CPU without really changing your code very much. So we'll kind of look at some techniques that allow you to do what we call parallel processing, solve multiple problems at the same time on the same CPU. All right. And And you can do this if you have a computer with a multi-core CPU, which all of you do. Even your phones are multi-core nowadays. Or alternatively, maybe some of you want to run the same computation on multiple machines, like on a small cluster of machines. It's going to be almost the same code, and I'll show you how to like distribute your computation across several machines in a small cluster. So it's not very hard. It's not hard to do with R. It's actually remarkably easy to do. So I'll talk about that next week. I'll also, if I can, I'll touch upon GPU processing, because nowadays a lot of computers come with powerful GPUs. These are graphical processing units, but which means it's a separate processor on your computer that is just designed to handle largely vector-based math operations, vector and matrix-based operations. So if you're doing a lot of stuff that's vector and matrix-based, um, which we did, for example, when we were doing like cosine similarity and stuff like that, then you could possibly use your GPU and it'll be a lot faster. And we'll see how much faster next week in class. If I can get that to work, I don't make any promises, okay? Because it's a little bit tricky to get this GPU processing working sometimes. So if I can get it to work, I'll definitely touch upon this topic as well. What else? Then I'm going to spend a little bit of time talking about coding style. So I'll talk about piping code. I showed a simple example of that last week with this native pipe operator, and I'm going to show you some other packages. I think some of you are familiar with like Margritter and some other packages that allow you to do piping. Um, and then I'll talk about things like how we can make interactive web-based dashboards using R. So if you have some data and you want to make a visualization and you want people to be able to interact with your visualization and have it change in real time, and you want to put this, let's say, on the web so people can come in over a browser and play with your interactions. I'll talk a little bit, I'll just introduce you to the tools that are used to create web-based dashboards for R. Okay. I'll talk about R server. This is if you want to have a centralized server that does computation. So you don't want to run the analysis on your own machine. You want to run it on a separate computational server, which is what we do in our institute, by the way. All right. And then I'll tell you about some other tools and tutorials which really explain to you how to write your code in a professional way for modern like data science standards. Okay, so I'll just introduce you to these tools. I won't go through them in much detail. I'll just kind of like briefly touch upon them, give you websites to go read more about them. There's some really nice tutorials out there. So for those of you who really want to go into a more data sciencey direction, these will all be really helpful things to know as you're moving forward, particularly in terms of heavy computation and coding style. Okay. So that'll be my fun, I'm calling them fun topics because you don't have to do a homework on them. That's great. And I'll just tell you, kind of give you some pointers as to where you can go next in your journey in business analytics and data science. All right, cool. So I'll send out a time. It might be Tuesday evening. That's my guess right now because I don't want to interfere with classes or final exams or anything that's happening next week. Um, and that'll just be a fun lecture. And I hope as many of you as you can make it, do try to make it. Okay. Okay, great. Um, any other questions? I think we're good for now. I don't see any new questions. I don't see any hands up. So we are still about 25 minutes away from the end of the class, but I'm going to end a little bit early. I know that a lot of you have exam week and final projects coming up. So I'll try to keep the homework light and easy, and it'll be the last homework. And I hope we can have a soft landing and an easy conclusion to the semester so that you can go back and focus on the exams and projects of your other classes, okay? I'm looking at you, my security students. All right, great. All right, thank you all very much. I hope you have a great, what day is it today? Monday. I hope you have a great week. Please stay safe. I hope the vaccines come out soon. I hope we all get vaccinated over the summer. Fingers crossed. And take care and talk to all of you soon. Okay, bye-bye.